Let us go on to a slightly more difficult problem. So, this says there is a constant volume tank which contains 20 kg of air at 1000 Kelvin. Okay, so there is a tank shown here, it has 20 kg of air at 1000 Kelvin, and a constant pressure device which contains 10 kg of air at 300 Kelvin. A heat engine is placed between the tank and the device, and it extracts heat from the high temperature tank, produces work and rejects heat to the low temperature device. Determine the maximum work that can be produced by the heat engine and the final temperatures of the air in the tank and the device. Okay. So, what we have is a tank which contains 20 kg of air at 1000 Kelvin, and we have a constant pressure device which contains 10 kg of air at 300 Kelvin. So, this is initially at 1000 Kelvin, this is at 300 Kelvin. There is a heat engine which is placed between these two. It extracts heat from the high temperature tank, so it is taking heat from here and produces work over here and rejects heat to the low temperature tank over here. We are asked to determine the maximum work that can be produced by the heat engine and the final temperatures of the air in the tank and the device. So, that is essentially what we want to find out, maximum work and the final temperature of air. So, in the previous cases what we are talking of is reservoirs where when you remove heat from the reservoir, the source and the sink, this A and B, in all the previous problems when we talk of the Carnot cycle and so on, when you remove heat from the reservoir remains at the same temperature because we sort of consider them as infinite. For example, a close approximation would be, for example, the ocean or the atmosphere, where if we run a small engine and we give out heat, the temperature of the atmosphere does not change. Or we have the ocean, we give out a small amount of heat or extract a small amount of heat, the temperature of the ocean taken as a whole does not change. So, we have been talking of those kind of systems so far. In this case, we have a finite system. So, over here our source is air at 20 kg of air at 1000 Kelvin. So, this 20 kg of air at 1000 Kelvin, as I extract heat from it, what I would expect is that the temperature of this air reduces. Similarly, I am rejecting it to some amount of air, 10 kg of air at 300 Kelvin. As I give heat to it, I would expect that this air would become hotter. Over here it is a constant volume system, it is rigid. Here I see it is a piston cylinder arrangement. So, as I give heat to this, what I will expect is that this piston also moves to the right. So, this is essentially what I have. So, what I can already say about it is the maximum work which I can get will be if I run a reversible engine. I run this in a cycle, I run a reversible engine, that will be the maximum. The second thing which I know is that when will this engine stop to work. So, the engine will stop to work when there is no temperature difference between the source and the sink, because then the engine will stop working. So, if the temperature of A and the temperature of B become equal, and that will be the final temperature. So, when they become equal, that is when this engine will stop working. So, that is also something I know. So, finally, I can write that the temperature of A will be the temperature of B equal to some final temperature F Tf. So, for A, we have initial temperature is given as 1000 Kelvin. Mass of A is given as 20 kg. This working substance in A and in B is air. I am going to assume it is an ideal gas. The mass, okay, in B the initial temperature is 300 Kelvin. Mass in B is 10 kg. So, this is a constant volume tank. So, it is rigid, okay, constant volume, which means any process which this air undergoes is a constant volume process. So, I am going to assume that this is a constant pressure process in B because it is a piston cylinder arrangement. So, A I have a constant volume process, in B I have a constant pressure process against from what it looks like against some ambient pressure. So, this engine is only taking heat from this A. So, there is no air from A actually coming into the engine or air going into B from here. So, each of this is a closed system. So, I can use the first law for a system undergoing a process. So, this is undergoing a cyclic process, the engine itself. It is taking only heat from here, there is no mass transfer here, there is also no mass transfer here. So, between these two, there is only heat transfer taking place. So, let me write the first law for A. So, A is considered as a system because it is rigid, there is no mass transfer, there is heat transfer. First law for a system undergoing a process, we know the first law for a system undergoing a process is essentially del Q, dE is del Q minus del W. The system itself is fixed, there is no change in potential and kinetic energy of the system. So, instead of dE, I can write this as du. Now, if I look at this system A, I know it is a rigid system. There is no displacement work because the system itself is not becoming bigger or smaller. There is no shaft work, I do not see any shaft. There is nothing coming in or going out, there is no flow work, there is no electric magnetic work and so on because it is only air. Therefore, essentially any work is 0, which means I have del Q is equal to du. This is an ideal gas. So, I can write this as, I am going to assume a perfect gas with constant Cv. So, I can write this as mCv into dt for A. So, that is an expression which I have. I know the initial temperature, I do not know the final temperature. The initial temperature is 1000, final temperature is some Tf. So, that is something which I have. So, let me also write the first law for system B. I have the initial same expression. So, there is no potential or kinetic energy change, the system is rigid, I mean it has a piston, but the system is stationary. So, there is no change in potential kinetic energy. So, I can write this, which is the first law for a system undergoing a process. In this case, there is work being done because this piston is moving out. There is heat being transferred, that is del QB. So, there is PdV kind of work, it is a constant pressure process. So, this del W is essentially PdV. I can also write this as du plus PdV plus VdP because Tp is anyway 0, pressure is constant, dP is 0, essentially I am just adding 0, it is fine. So, this is d of PV and this is d of u. So, that is d of u plus PV, which is dH. We have seen this earlier. So, when you have a constant pressure process, what we see is that the heat transferred is essentially the change in enthalpy. We have seen that earlier, but we just re-derived it anyway for convenience. So, again the substance here is air. I am going to assume that air is an ideal gas, which means I can write dH as m into some Cv times Cp times dt. So, this is some m times Cp times dt if this is an ideal gas. So, I have an expression for del QA and del QB. What we are asked to find out is the maximum work that can be produced by the heat engine and the final temperatures of the air in the tank and the device. So, that is essentially what we are asked to find out. So, if I apply first law for this engine, first law, the engine is undergoing a cyclic process. So, essentially cyclic integral of del Q is cyclic integral of del W. Taking QA coming in as positive and QB going out as negative. So, of course, the expansion of this is also essentially sigma of del Q is sigma of del W. I am just going to call this as W. This is del QA plus del QB with the appropriate sign convention which is required. Del QA is positive, it is heat coming into this engine. Del QB is negative, heat going out of the engine. Since I know already that this is coming in, this is going out, what I can do is I am usually doing this, taking the negative sign out because I know it is negative, and then I will only write the positive value over here. So, I can get del W by integrating this expression. Sorry, I can get W by integrating this expression. So, integral of del QA plus integral of del QB if I am integrating this expression, or if I am taking this already as positive, then I have the negative sign here, but either of them is okay. So, what I need to be careful about is whether I have taken into account the negative sign already or not. So, here del QA over here is heat going out of the system, which is negative for this and it is positive for this. So, that is mCV into dt, that is m of A, Cv of A, dt of A, and I have del QB, which is heat going out of, I am now looking at it from the perspective of this engine E over here. This is heat coming in, which is positive. This is heat going out, which is negative. So, I need to take into account the negative sign when I am dealing with this term here. So, this is mCp m of B, Cp of B into dt of B. So, I am taking a negative sign here to, because that is a negative quantity there. So, let me integrate this. I am assuming m is constant, which is, I mean, it is not really an assumption, I know m is constant. I am assuming Cv and Cp are constant. So, I get essentially ma Cva into dt from initial to final. This is after integrating delta t. I know the initial temperatures. If I knew the final temperature, I could find out the work done. So, the question is there any way of finding out the final temperature? I am asked to find out maximum work, not just the work. So, for maximum work, the engine must be reversible. So, if the engine is reversible, then what we know is that this should be applicable. So, I had expressions for del QA which is mCv dt, QB. So, what we are seeing is that then, so when we are writing it, for example, in the Carnot cycle, we say QH by TH is QL by TL. What we mean over here is QH is also positive, QL is also positive, because both of these are positive. We are looking at temperatures at the absolute temperature scale. So, the denominators are already positive. So, we need to make sure that the numerators are positive. So, we have here mCv dt by TA, which is okay, and we have mCp dt. This is A, m of B, Cp and Cv are both for air, into dt of A, this is dt of B by Tb. So, the way this is written, the temperature of A is going to reduce. So, dt will be final temperature minus initial temperature, which will be negative. Over here, the temperature of B is going to increase because I am giving heat to the piston cylinder arrangement. So, this will be positive. So, they are written in such a way that one of these terms is negative, one of these terms is positive. So, but when we are writing it in this form, we need both to be either positive or negative. So, let us put a sign on one of the sides. So, we get this. So, we can integrate this. Integrating, what we get is that this is essentially m of A into Cv of A into ln ln Ta, going from initial temperature to final temperature, is equal to mass of B into Cp into ln Tb, going from initial to and then the minus sign is still there. So, m of A is 20 kg. I need Cp and Cv, well, I do not need Cp and Cv, I need Cp by Cv. So, Cp by Cv is essentially gamma. So, this is a diatomic gas, it is air, gamma is 1.4. So, I will take the Cv to the other side and that is there. Let me take Mb to this side, divided by mass of B is I think 10, is 20 divided by 10 into ln of T final, which I do not know, minus ln of T initial, which is 1000 Kelvin, is equal to minus of Mb, I have already taken the other side, Cp by Cv is 1.4 into ln of Tb final, which is Tf essentially, minus ln of T initial is 300. So, I have this is 20 by 10, which is essentially 2, 1.4 divided by 2 is essentially 0.7. So, I have this expression. So, ln of T final plus 0.7 ln of T final. So, that is essentially 1.7 ln of T final. This goes to the other side. So, ln of 1000, and this minus goes in. Did I take the signs correctly? So, this was minus, this became plus, okay. This goes to the other side, it is ln 1000, and this minus into minus is plus. So, that is ln of 300. So, I need to find out what is T final from this. So, I have ln of TF is essentially 7.41. So TF is exponent of this, which gives me, I think, about 1666.6 Kelvin. That be right? Okay. Let me come back to where I was. I need to find out work. Work is m mass of A. So the work done is essentially del QA minus del QB, where each of them is positive. Integral of these. So essentially we have MA, which was 20 kg, into CV. CV is essentially R by gamma minus 1. R is R bar divided by molecular weight. So we have done this calculation before, and typically for air we can take R as either 287 or 288, which gives us a CV. So let me take R as essentially 287 joule per kg Kelvin, which gives me a CV of about, if I take as 287 by 0.4, gamma is 1.4. This gives me a value of 717.5 joule per kg Kelvin. Cp is gamma times this, so this into 1.4, which gives me a value of about 1004.5 joule per kg Kelvin. So I have 20 into CV, this is m into CV, into delta T. So if I wrote it in this fashion, this would be negative, and this would also be positive. So the work would turn out in this case to be negative, which is essentially the work for the engine, because it would actually turn out to be negative, which is not going to be correct, because I have written this from the perspective of this system over here, not from the perspective of the engine. So, but as long as I know that, it's okay. So this will be T final minus T initial. T final must be lower than T initial, so clearly my value is wrong. Okay. So I have made some mistake in the calculation of TF. Let me go back and try to fix it. Where we have air in a sort of a rigid tank, which is at a high temperature, and we are running an engine between this tank and a piston cylinder arrangement, which is at a lower temperature. So we were solving this, and we saw we had all of the equations right. At the end of it, I got an answer which was higher than the initial temperature. So I assumed that the problem was wrong. So it turns out the problem is correct after all. So what I missed out is a 0.7 over here while taking stuff from the left hand side to the right hand side, or actually while removing the brackets. So now it turns out that this is not correct. So let's just look at what the answer would be. This is not correct either. This comes out to be 10.9. This is 10.9 divided by 1.7, which is 6.41, and this is exponent of 6.41, which is about 609 Kelvin. Okay, so we have the final temperature now. You are going to possibly see this as one continuous video anyway. So the work is mod of heat transferred in minus heat transferred out, or if I don't want to use the mod, I can just use sigma del Q. So del QA plus del QB, and that would be correct. but what I need to keep in mind is that initially when I wrote the del Q values, I wrote it for this system A and for this system B. So, as far as the engine is concerned, the signs would be reversed. So, for this system the heat transfer out is positive, which is what we get because dt would be positive, dt would be, the heat transfer out for this system is negative and dt would be negative because it is heat transfer out of the system, whereas for this engine it would be positive. So, there would be, I would need a negative sign in front of this del QA for the engine. Similarly, what I found out as del QB is for this system where heat is entering the system and it would be positive. For the engine that would be reversed. So, what I had written here as del QA minus del QB, if I just did it, what I should possibly do is put a mod in all of these so that I get the correct signs. This expression is correct provided I use the correct signs for del QA and del QB. So, here if I used del Q as if it was for the rigid body on top, I would get the wrong signs here, but that is possibly still okay. I would just have to put a negative in front of this, but I guess the easier way is just to do mod for all of these, because then there is no confusion at all. So, just sigma del Q with the correct signs for del QA and del QB as whether heat is entering or leaving would give me the right answer, but I will just do this in this way anyway. So, I had Ma into CVA, so that is mass of air into CV into the final temperature minus the initial temperature, but I have a mod anyway, so I will take the difference. So, I will take initial minus final because I want a positive value. I have already taken out the negative sign here, so I should have a positive value here also. The mass there was 10 kg, Cp is 1004.5 joule per kg Kelvin, and the temperatures are 609 minus 300. Again, I have already taken delta T is final minus initial, but I have already taken out the negative sign and I am only taking positive values on both sides. So, let us see what this comes out to be. So, this is about 5.6 megajoule. It's about 3.1 megajoule. So, this comes out to be about 2.5 megajoules of work which we can extract from this device. So, we are asked to find out the maximum work, which is what we have found, and the final temperatures of the air, which is also what we have found. So, the final temperature is this value, and if this work was done reversibly, we would get about this much amount of work from this device.